In this video, we want to take a look at multiplying and dividing Taylor series. Now, adding and subtracting is pretty simple. Multiplying and dividing is not quite so simple, but it's not impossible. If you think about how you multiply polynomials together, right? Let's say binomial times binomial. There's this thing we call FOIL, right? First outside's inside last. Essentially distribute everything in the first thing with stuff in the second thing, and if it's bigger polynomials, it's bigger FOIL. Well, we got infinitely long polynomials, so we're going to do really big FOILs. So I want to start off with an example. Again, two functions that we've worked with a zillion times in the course of these videos I'm making here. E to the x divided by 1 over x. Now, I'm going to do this two different ways. I'm going to do it as a multiplication, and I'm going to do it as a division. But first of all, as a multiplication, I can think of this as e to the x times 1 over 1 minus x. In terms of Taylor series, or Maclaurin series in this case, e to the x is 1 plus x squared over 2 plus x cubed over 3 factorial plus x to the fourth over 4 factorial plus and so on. And then the 1 over 1 minus x is the ice cream theorem, right? This is 1 plus x squared plus x cubed plus x to the fourth and so on. And what I want to do is I want to multiply them together. So every term in this first series has to be multiplied by every term in this second series. So first of all, but the way I'm going to do it is I'm going to look for similar types of things. So for instance, the only way that I'm going to get a constant is if I have the constant here times the constant there. So 1 times 1 is 1. In order to get a linear result, I could have a constant times a linear, or I could have a linear times a constant. As soon as I get to the squareds, I'm not going to have linear anymore. So there's two ways that I could get just x to the first power. So that's the 1 times this x, and the x times that 1. So there's the x and the x. Now for x squareds, I'm going to have three ways, it turns out. Because I could have this 1 times that x squared. That's that x squared. I could have this x times that x. That would be x squared. There it is right there. And then I could have this x squared over 2 times that 1. And so this is x squared over 2 right here. And so there's three terms that have x squareds in them. And then for x to the, what's next, 3, I could have the 1 that's here times the x cubed. There's that x cubed. I could have the x that's here times that x squared. There's x cubed. I could have the x squared over 2 times that x, that's x cubed over 2, and then I could have this x cubed over 3 factorial times that 1. There it is, right there. So I had one way to get a constant, I had 2 ways to get a linear, 3 ways to get a quadratic, 4 ways to get a cubic. There's 5 ways to get x to the fourth powers, right? 1 times that x to the fourth, x times that x cubed, x squared over 2 times that x squared, x cubed times that x to the fourth times that 1, and there's all the results right there. And then you go plus, do all the fifth powers, and then so on. Now, textbooks generally give a formula for how to calculate the nth term of the polynomial, of the product, right? The polynomial, or the Taylor series. And they say, look, you're going to have something from here times something from there, and the bigger power of x you're looking for, the more more combinations you're going to have to make that up. But it's just a FOIL. It's just everything in here gets multiplied by everything in there, and then you collect your like terms. Right? So anyway, collecting like terms now. The x times x is 2x. The x squared plus a half x squared is 2 plus a half x squared. And the x cubed is there's 2x cubes and a half x cubed and 1 over 3 factorial x cubed. So those all get added together times x cubed, and likewise x to the fourth. It's not difficult to do, it's just long, right? It's just a long process for multiplying Taylor series together. I also want to do division. So I'm going to do 2 division problems for you here. Rather than trying to typeset them, I'm going to do them by hand. I want you to see the whole process. We don't do polynomial long division very often, but I want to do it here. I'm going to do the same one, first of all, e to the x divided by 1 minus x. Rather than doing it as a product, I'm thinking of this as a quotient. So I got the e to the x. I'm going to turn that into its Taylor series. And then I'm going to divide that by 1 minus x. When I'm done with that, I want to do another example where I'm actually dividing a Taylor series by a Taylor series. This becomes a bit more complicated, but again, still possible. Here we go. Let's do this first one. Okay, so I've got the Taylor series for e to the x here, the Maclaurin series for e to the x underneath here, and I'm going to divide it by 1 minus x. Now, I should point out that when you learn polynomial long division, maybe in a pre-calculus class or something, we typically write our polynomials all in decreasing order. So biggest power first and all the way down. Well, it's hard to do that with Taylor series because there isn't a biggest power, right? It just keeps going. So I am choosing to write everything in ascending order, including the thing I'm dividing by. And so what I'm going to do is I look at the first term here and the first term there, and I say, what do I have to multiply 1 by in order to get 1? Well, it's 1. And so now I say 1 times this thing, that's 1 minus x, and then I'm going to subtract. And to subtract, I just change the signs and add. So the 1 minus 1 is 0, and then I get a 2x right here. Bring down the next term, 1 plus, bring down the x squared over 2. And now I say 1 times what is equal to 2x? Well, it's multiplied by 2x. And then take this 2x times everything there, so that's 2x minus 2x squared. And subtract. Change the signs and add. Those go away, and I've got a 2 plus a half times x squared. All right, bring down the next piece, x cubed over 3 factorial. I mean, technically I'm bringing everything down every time, except I only get 2 things that this combines with, and so the other ones you don't even have to really think about until it's their turn. Anyway, 1 times what is 2 plus a half? Well, or 2 plus half x squared, I need to multiply by 2 plus a half x squared. And I'm choosing to leave it like this just because I know what the answer looked like from the previous calculation. So I got 2 plus a half times x squared times this whole thing. So there's the 2 plus a half x squared. Here we go. This should be a minus sign. And that's in parentheses times x cubed now, right? Because the x squared times x is x cubed. Subtract. Change the signs and I add. And so now I've got 2 plus a half plus 1 over 3 factorial. That whole thing times x cubed. Bring the next one down, plus x to the fourth. And perhaps you can see what's going on here. Each time, because this is just a 1, it's really easy to figure out what do I need to multiply this by in order to get that. It's just that. Right? So this is going to be plus 2 plus a half plus 1 over the square root of 3, not the square root of 3, 3 factorial times x cubed. And when I multiply it, this is the same thing here. And then I've got minus that thing again, 2 plus a half plus 1 over 3 factorial. So what just happened here? 1 over 3 factorial times x to the fourth, because that was a cubed up here, times the x there. And change the signs and add. And this is just coming out exactly the same. I got 2 plus a half plus 1 over 3 factorial plus up here 1 over 4 factorial times x to the fourth. And so on, right? And I think we can see that in doing this, we end up with exactly what we had before of, where are we? There's the 2 plus a half x squared, 2 plus a half plus 1 over 3 factorial x cubed, 2 plus a half plus a, yeah, it's the same thing. Okay. That one was reasonable to do. Now let's try calculating the tangent by thinking, hey, I know how to do sine, I know how to do cosine, and I know how to divide. So let's do that. This is a bit more work, and the hope is that we can maybe see a pattern, maybe not. I may have to just say, well, we're going to get the first few terms of it. The 1 here makes it reasonably easy. Again, I have the Taylor series for cosine in here and the Taylor series for sine. Other way around, sorry. This is the sine in here and the cosine out there because I'm doing sine divided by cosine. So I say how many times does 1 go into x? It goes in x times. And then I do x times all this stuff. So I've got x minus x cubed over 2 plus x to the 5 over 4 factorial plus no. It should be minus x to the 7 over 7 factorial over 6 factorial. Come on now. Plus and so on. And then I subtract. Right? Now, because this is an infinite polynomial here, I've got all these infinitely many things that I need to subtract. And so as I subtract them, I'm going to change the signs and add. So this becomes a minus, and this becomes a plus, and this becomes a minus. And so these go away. And what do I have here? I've got 1/2 minus 1 over 3 factorial times x cubed. And here I've got, let's write it as minus 1 over 4 factorial minus 1 over 5 factorial x to the 5. And then plus 1 over 6 factorial minus 1 over 7 factorial x to the 7 minus and so on. Notice I chose to write this one here as I did. Sorry, I don't know if you can tell where I'm pointing. Right here. Because I could see a pattern. This was the smaller 2 factorial, bigger 3 factorial. Smaller 4 factorial, bigger 5 factorial. Smaller 6, bigger 7. Each one I'm writing the smaller factorial first. And so in order to do this one for x to the 5th, that way I had to factor out a minus sign to make that a positive 1 over x to the 1 over 4 factorial. Okay. So that first thing is an x, and I've done all this. Now, what's the next term? The next term is how many times does 1 go into this thing? So this is going to go plus 1/2 minus 1 over 3 factorial times x cubed. And then you have to multiply this times everything here. And it starts to get big fast. And I'm not going to do much more than this right here, because this is going to be exactly what it needs to be in order to cancel out the x cubes there. And then it starts getting really unwieldy. So this times the minus 1/2. So I got minus 1/2 times 1/2 minus 1 over 3 factorial. And this is now x cubed times x squared, so that's going to be an x to the 5th. And then plus and so on. What do I have? I've got 1 over 4 factorial times 1/2 minus 1 over 3 factorial x to the 7 minus and so on. My face is in the way. Let's go over here. Subtract. This goes away, 0, and then you got to have all of this stuff, and boy, it gets big fast. So subtract. So this is minus, this is plus, this is minus, this is plus. Yeah. So those go away. What do I have here? I've got 1/4 minus 1 over 2 times 3 factorial minus 1 over 4 factorial plus 1 over 5 factorial times x to the 5th. And then what's here? I guess I'm going to go with plus here. So minus 1 over 2 times 4 factorial. What's that? Plus 1 over 3 factorial, 4 factorial, plus 1 over 6 factorial, minus 1 over 7 factorial times x to the 7, and then so on, right? It gets big pretty fast. But I could keep going, right? I could keep going. I could keep generating more terms in this fashion. I don't think it's worth it, but I just want to point out that it can be done. Okay, you can multiply Taylor series. You can divide Taylor series. One thing, though, that we do want to mention here is that division definitely changes, has the potential of changing the interval of convergence. Because notice the tangent curve, the tangent function has asymptotes at all the odd pi over 2s, at 1 pi over 2, 3 pi over 2, minus pi over 2, minus 3 pi over 2, right? All the odd pi over 2s. There's a vertical asymptote. So the Maclaurin series that I'm generating centered at 0 certainly isn't going to have a radius of convergence any bigger than pi over 2, right? I would expect the convergence to be from minus pi over 2 to plus pi over 2. Stop at those two vertical asymptotes. In multiplication, the only issue is what are the intervals of convergence of the two things that you're multiplying, and you got to take the smaller one, would be the interval of convergence of the product. But division, you might not have, sine doesn't have any vertical asymptotes, cosine doesn't have any vertical asymptotes, but cosine is 0 every once in a while, and so when you're dividing by 0, that causes a vertical asymptote for the tangent. So even though sine and cosine converge, these Taylor series converge for all x, tangent doesn't. Tangent's going to be just between 0 and, between minus pi over 2 and plus pi over 2. Okay. Anyway, next we got to take a look at derivatives and integrals.